We continue with our study of algorithm design techniques. We had looked at some examples which for which we used this divide and conquer strategy. We also looked at sorting. I mean, this strategy applied to sorting. We gave a lower bound of n log n for certain sorting based algorithms. We continue along the same vein. In fact, we look at yet another problem which is amenable to divide and conquer. Okay, this problem comes from computational geometry. So it has the basic field is a bit different, but the same strategies, algorithm design strategies apply to even this field. Okay. So the problem is this: the input is a set of points, okay, in the plane, say, okay, the output. So I want the closest pair of points. Okay, so given some points, I can compute the distance. Okay, you can compute the distance, and among these points that you are given in the plane, you want to find the closest pair. Okay. For instance, the points could be given with the x, y coordinates. That's what we'll assume. So for each point, I give you the x and y coordinate, and let's say there are n points, and given these n points with their x, y coordinates, I want to find a pair of points which are closest to each other. Okay, so given any 2 points, there's a distance, right? The distance is square root of x1 minus x2 squared plus y1 minus y2 squared, the usual notion of distance that you have in the plane. So for each pair of points, there's a distance, and there are n choose 2 distances, right? So between these pairs of points, if I have n points, there are n choose 2 distances, and I want to pick the minimum distance and the points which actually witness this minimum distance. Okay, so there is an obvious way to do it, which is to compute for each pair the distance. Right? For each pair, you compute the distance. Now you have n choose 2 distances, and you find the minimum. Okay, that takes n choose 2 time. Right? Can you do faster? Can you do better? So for instance, do you really have to compute all distances to find the closest pair? Well, that's the big question here. And well, the answer is no. Okay, if the answer were yes, then I guess I would not be discussing this problem here. Okay, it's just far too simple. So the answer is yes, and in fact we'll do it much faster than n squared. So somehow you don't really need to compute all pairs, distances of all pairs. Okay, that's the moral of the story. Okay, so let's see how we go about designing such an algorithm. Well, on the face of it, if you think a bit, you start to wonder why do I need to compute every pair of distance? What kind? Can I, for instance, look at geometry of the points? Certain distances, maybe. Okay, there are many ways of thinking about it. You should also be thinking of an inductive approach. Okay, which is supposing I remove one point and compute the distance, shortest distance between the other points. Okay, now adding this point, can I get rid of some points? Well, maybe yes, maybe no. So let's look at this approach. This will not be the approach we'll finally follow, but This is something that I want you to think about for every problem. Okay, so that's the reason I just want to go over this again. Okay, so the classic sort of inductive approach to this, to any such problem, is remove a point, okay, recurse on the rest, put the point back and see what you get. Good. Okay, so let's see, this is the point I have removed. Okay, the points sit in this, let's say in this region. There are other points. Okay, this huge big star, this dot, is what I have removed. Okay, now I find the smallest distance. Good. Now what can I do? I mean, how do I compute the shortest distance? Well, it looks like, I mean, the obvious thing is to compute distances from this to every other point, but that is, well, that's not too great, right? You're back to the original, to where you started, because there are n minus 1 such other points, and you will compute n minus 1 distances. Okay, and this recurrence, you will see, will lead to an order n squared solution, because your recurrence will be Tn is n minus 1 plus T of n minus 1. Okay, this will lead to order n squared. Okay, you can check this. Well, can I get rid of some of these points now? You could, if you could do the following. Supposing the minimum distance here, okay, over the entire set except this point is delta. Okay, the minimum distance you have calculated recursively is delta. Then you know that any point, okay, the points that are actually in contention are points in a circle of radius delta around this point, right? Only points in this circle are in contention. The other points are, well, too far away. If you can quickly compute these points, then you are in business. Okay, I took n minus 1 time to extra time, but supposing I can do this much faster somehow, I don't know how, but if you can compute this much faster, then you are in good shape. Okay, then you can maybe reduce this n minus 1 somehow to something else. Okay, for instance, if you reduce this to log n, you are in really good shape. Okay, then maybe you can push this further. So your thinking should be along these lines. Okay, how do I cut this n minus 1 down? Okay, so before we go further, let's do this in one dimension. So what does that mean? You are given a line and some points. Okay, you are given some points, right? Let's see, and you want to find the closest pair. Okay, along this line, you want to find the closest pair. How will you do this? Well, yeah, I think at least some of you should now see that you don't really need to calculate all the n choose 2 distances. You know, there are n points, there are n choose 2 sort of distances. Maybe you don't really need to do n choose 2. Okay, look at all n choose 2. So how would you sort of do this? Well, the thing to notice in all these things, you know, you need to notice something about the problem, some property of the problem that sort of pushes you up. Okay, that lets you do things faster. So in this case, okay, in this case, well, the thing to notice is that supposing I'm looking at this point, the only candidate points are the adjacent ones. I mean, these are the only candidate points. If for each of these points I can identify these candidates, then I'm done, because I need, for each point I need only to check 2 distances. So that leads to 2n, right? So for each point I need to check 2 distances. So for n points I need to check 2n distances. But which 2? That's a big question. Okay, for this point, how do I find these 2 which are neighbors in some sense? Okay, if I can do that, then it's just two end distances and, well, looks linear. Well, how do I find these two? Maybe just sort them. Okay, so in one dimension, sort. Well, once you sort them, look at them in increasing order of from left to right, and for each point, look at the previous and the next one. Compute these distances and choose the minimum. Okay, then you can choose the minimum by scanning these points. Okay, sorting takes order n log n. Okay, so we started out with n choose two distances, but really the time taken is order n log n. Okay, sorting dominates this procedure, and if I sort of first sort it and then I do this, then it takes the time taken is n log n. I have reduced it from n squared to n log n. Okay. There are some morals in this story. First one is you should always try a simpler problem. You are given this problem in 2 dimensions. It always pays to first check out what the problem means in 1 dimension. Okay, you learn a little bit. That's the first thing, and you at least now know that maybe it's possible to do it in less than n choose 2 time, because in 1 dimension certainly you can do it in n log n time. Okay. The question one asks now is, what about 2 dimensions? Is there something like sorting that I can do? Okay, which will help me out? Well, the answer is actually yes, and let's see how this is done. It's quite a smart algorithm. Okay, so we will try and apply a divide and conquer approach. Okay, reasonably blindly, but as we proceed, we'll start to use some tricks that will speed up the computation. Okay, so the first step is something you can think of. I want to divide the points into 2 parts. Okay, find the minimum on the left part and find the minimum on the right part. Okay, and then once I find the minimums, now I'm going to use these minimums to compute the overall minimum. Will this help? Will this not help? Well, we'll have to see. Okay. Before we do this, I think it's also illustrative to do this on the line. Okay, we first sorted and found out the minimum, that was n log n. Let's see what this gives. This divide and conquer strategy gives on the line. Okay, so I am given these endpoints. Okay, can I get something? Can I do something better? What would the divide and conquer strategy be? Well, divide the points into 2 parts, one on the left, one on the right, and recurs on both. Okay, and what? Okay, once we get the minimum distance from this and that, now the only sort of thing that we have not checked is if the minimum distance between points on the left and a point on the right. Right? I find the minimum here, find the minimum there. Okay, and then the only distance I need to now compute is a point on the left. Okay, the last point on the left, the first point on the right. Find this distance and check this against the minimum that I've computed. So I found, let's say, delta L, delta R, and this is delta. Okay, I need to find this minimum. Okay, so once I compute delta L, delta R, and delta, I just check the minimum of these and return the minimum of these 3. I need to make sure that I find this point on the left recursively, and I find this point on the right recursively. Okay. So again, this if I want to do it by divide and conquer, then I need to strengthen the inductive hypothesis, which is that not only do I find minimum distances, but I also find the last point, the rightmost point and the leftmost point. Once I do this, then I can sort of put these two things together to get a solution. Okay. I don't want to get into this in detail because the problem here is again splitting the input into two parts. You know, how do you split this into two parts? Well, you need to split it into two equal halves, then you need two halves. Well, then you need to find the median. Okay, that takes linear time. So if I look at the recurrence, it looks like Tn, okay, is 2Tn by 2, okay, plus order n, and this we know is n log n. Okay, the solution to this is order n log n. This is the time taken to find the median and divide. This is the divide step. So this doesn't really use sorting in any sense, except to find the median. So this is another way of sort of doing this using just plain divide and conquer on these points on the line. Okay. Let's do this to points in the plane. Okay, you are given points in the plane. I'm going to divide this into two parts. Okay, let's say based on the x coordinate. Okay, the first n by 2, the leftmost n by 2 points will form one set, the rightmost n by 2 points will form the other set. I recursively find minimum distance, closest pair of points in the left, closest pair of points in the right, and now I need to find the closest pair for the entire thing, and let's see if this can be done fast. That's the goal of this lecture. Okay. So okay, so here let's see, my points lie in this blob. I've divided it into two parts. Okay, there are n by 2 points here, so this is the left and that's the right. Good. There are n by 2 points here, n by 2 points here. Okay. Now I find the closest pair of points on the left, closest pair of points on the right. Let's say that delta L is the closest, is the minimum distance on the left, delta R is minimum distance on the right. Okay. Let delta be minimum of delta L and delta R, which is the smaller of these two. Okay. Now I need to find closest pair, and I know that if at all there are candidates for the closest pair, it has to be that one point has to be on the left and one on the right. Okay. Any candidate pair has to be of this form. They can't both be on the left or both on the right. One of them has to be on the left and one of them has to be on the right. Okay, what else can we say? Okay, let's also sort of at the same time keep the recurrence in place. So I'm looking for, so Tn, if Tn is the time, I have already done this. Okay, plus what? Well, I would like this ideally to be, if this is say order n, then I know this recurrence is n log n. I'm in good shape. So this is the amount of work that I'll need to find the closest pair, one from this side and one from that side, where one point is from this side, one point is from that side. Suppose I do it, well, the natural way is to just pick every point on the left, every point on the right, and sort of find the distances, right, for every pair. This could be as large as, well, there could be n by 2, there are n by 2 points and n by 2 points here. That gives rise to n squared by 4 pairs. Okay. So if I compute n squared by 4 distances, I'm sunk. Okay, that's just too much. In fact, we'll be back to our usual n squared. So we'll be, you can check that we'll compute all distances, all pairs of distances, n choose 2 distances. So this is not what we want to do. Okay, so how can we speed things up? This is the question that you need to answer. Now at this point, it is left to your ingenuity. Okay, it's left to a little bit of luck, but there are no clear, it's not as if, at least I don't know of anything that I can teach you which you can use. Okay, this is left to just, you know, your own intelligence and perseverance, you can try small problems, small examples, etc., etc. But the ideas from this point onwards are completely new. Okay, they are problem dependent. Okay, depends on the problem, and there are no general techniques that I can tell you which you can use. Okay, there are no formulas that you can apply, and this, in fact, is the beauty of this this field. That it's not that I pump you full of ideas and then you're all ready to take on a problem. That's not the way it works. Okay, each problem has a flavor of its own, and each candidate also has his own capabilities, and each person has his own capabilities and his own. And there's a good chance that if you try this problem, you will come up with your own algorithm, your own fast algorithm maybe. So from this point onwards, I'm going to tell you a few tricks by which we'll reduce this. These observations which I'll make will sound reasonably simple initially, but these you have to find on your own. Okay, there is no teacher can teach you this. You have to learn it yourself. Okay, it just depends on your analytical skills. Good. So let's now get back to this problem. Yeah, the first thing I'm going to note is, where do these supposing I have these candidate points on the left and right. Now where can they lie? Okay, let's look at this. So this is my dividing line. Okay, dividing vertical line. Things on the left. Where can they lie? Well, they cannot. They all have to be. Well, let me draw a straight line if I can here. Okay, they have to be within a distance delta of the middle of this middle point. Similarly on this side. Okay. If a point lies here, then the distance between this point and any point on the right is greater than delta. Right? If it lies on this side, this point and anything on the other side, the distance is greater than delta. So I can forget about these points. So the only points of interest to us are points in on these two small bands on either side of the middle line. Okay, each of these bands has width delta. Okay, these are the points of interest. Okay, that's the first observation we make. Okay, this is fair. So far, it's all fairly simple. Okay. Now, just this is not enough. Okay, the same problem could apply in the sense that all n by 2 points on the left could lie in this band, and all n by 2 points on the right could lie in that the other band. In which case, we are again back to computing n squared, roughly n squared distances. Right. Here's the other smart thing. Okay, the intuition is this. So let's magnify this the small band around the center. Okay. So here's the central line, and here are the two bands. Right. So this is delta, and this is also delta. Okay. So when I look to the left, okay, if I take any point here, okay, if I take any point, then I know that if I draw a circle of radius delta around this, there is no point inside this circle. The reason is this closest pair of points on the left, this is the left, okay, is delta. So there is nothing closer than delta to this. There could be something at distance delta, that's fine, but there is nothing closer than delta. So these points are actually spread. There can't be a large number of points clustered together. They are all spread out nicely, okay, at distance delta. Similarly, the points on the right. We would like to use this fact. Okay, this is point number one. That these points on both left and right sort of spread apart. Okay, so there cannot be too many points close by. Somehow we need to use this. Okay. What else can we say? Well, let's look at this point on the left. Okay, so let's look at this point on the left. What about points on the right? Where can they lie? So let's draw this line. Well, I know that any candidates for this point will lie while this doesn't look like a square, but think of this as delta, okay, and that's delta. So any candidates for P must lie within either this square or this square. Okay, please train your imagination and imagine this to be a square. Then any candidate for this point must lie either in this square or that square. Okay, they cannot be. If it's outside here, then the distance is greater than delta. Okay, in fact, distance to this line is greater than delta, so to this point is also greater than delta. So everything has to lie here. That is the first thing. The second thing, we know that if I take any point here, then this precludes many points from appearing in a region of size delta, right? If I have a point, in there, then in a circle of radius delta, no other point appears. So there cannot be, I mean, intuitively one feels that there cannot be too many points inside each square. Okay, this is a delta by delta square. If there are too many points inside this, okay, there are bound to be 2 points which are close by. I cannot have every point as far away as delta. This is what we are going to use. But how do we use this? Okay, intuitively you feel that there cannot be too many points inside the square. Okay, the reason is essentially this, that if I have a point, there is nothing within a distance delta of it. Good. So how do we put this intuition into practice? We use a very simple principle that you have heard many times. It seems very simple, but putting it to practice often requires some thought. Okay, the principle is called the Pigeonhole Principle. Well, what does it say? It says that if there are n plus 1 pigeons and there are n holes, and you stuff these pigeons into these holes, then at least one hole must have 2 pigeons. Okay, there are more pigeons than holes, so if you stuff these pigeons into holes, then at least one hole must contain 2 pigeons. Very simple principle. We all immediately understand the statement, but often very difficult to figure out where to apply and how to apply. Okay, some really nice problems have solutions based on this principle, which smart people have not figured out. So let's go back to the square problem. Okay, so I have this square of size delta. Okay, and I know that if I have any point in this square, then no other point is within a circle of radius delta, which means given any 2 points, the distance is at least delta between any pair. Okay, so the distance between any pair of points in the square is at least delta. How many points can I put inside the square? That's the question. Well, here is the trick. What you do is divide this into 4 parts. These will be our holes. We'll have to see what the pigeons are. Well, what is the maximum distance inside the small square? Well, this small square has side length delta by 2. Okay, the maximum distance is along the diagonal, which is square root of delta squared by 4 plus delta squared by 4. Okay. Okay. So this is square root of delta squared by 2, right? It's just twice this, which is nothing but delta by square root 2, which is strictly less than delta, which is what we want. So if I take one of these small squares, then the maximum distance is delta, which means I cannot have 2 points sitting inside this small square, right? If I take any 2 points, the distance between them is less than delta. So at most 1 point can sit inside this small square, which means in the big square, I can have at most 4 points. If I say that the distance between any pair of points is at least delta, inside this big square, I can have at most 4 points. Okay, this is the big trick. that we'll use. Okay. So this is the trick we'll use. So let's get back to the original picture here. Original picture. So I have P, and how many points on the right do I have to really compare? Well, 4 inside this. Okay, there could be at most 4 candidates in each square. If at all, right? 4 or less than equal to 4, could be less. So which it looks like as of now, for each point I need to at most look at 8 other points and compute distances, right? And this certainly looks to be linear, right? If for each point I need to compute at max, as they say, okay, 8 other distances, then A10 distance is what I need to compute, and in my recurrence I'll have 2Tn by 2 plus A10, and this is n log n. Okay, how do we do this? We are still not done. I mean, we have all the ideas in place now, except implementation. Smaller, there are smaller implementation details that we need to worry about. For instance, for each point on the left, how do you compute these 8 points? Okay, you have to do this fast. Remember, you can't take a lot of time to. If you look at all the points for each point, then you're sunk, because that's n squared already. Okay, but again, looking at this picture, you should sort of you should again get ideas. So let's go back to this picture. So here is the point. The 8 points are somehow located in the neighborhood of this point. Okay, they are at distance delta from here, delta from here. These are the points that I need to, and this window I'll need to shift up. Okay, so let me put up another picture, and after this picture, hopefully the algorithm will be clear. Okay, so here is my center line, and here are these various points. Okay, on the left and on the right. Here are these various points. If I take any point on this side, okay, if I consider this, then I only need to look at a window of size 2 delta, delta on this side, delta on that side. Okay, this is what I need to do. As I go up, okay, if I look at this point, this window shifts up. Okay, it's somehow, if I can scan them upwards in this order, scan from bottom to top. Okay, if I can scan these points from bottom to top, somehow this window also keeps shifting from bottom to top, and it again looks like I can do this efficiently, right? All we need is these things sorted by y coordinates. If I have these points sorted by y coordinates, by the y coordinate, then I can scan the left side from bottom to top, the right side from bottom to top, and I can maintain this window easily. Okay, this is the last trick in the algorithm. Again, there is a detail left. Okay, so if I have these points sorted by their y coordinates, right, then this is what I do. I start looking at the points on the left in that band, in the narrow band. I look at these points, look at them in increasing y coordinates, right, and for each point I also maintain this band of this sort of window on the right. Okay, so when I look at a point, I have a corresponding window on the right. When I move to the next point, I correspondingly move the window up. Okay, this is all I do. So somehow I need to move this window up, and you can see that it should not be too difficult to move the window up. Okay, and the time that this takes is linear, and it's very similar to the merge sort idea. Okay, the window moves up each time. Okay, on the left, each time a pointer moves up. Okay, on the right side, the window could move up, but it can move up only n times. The window can move up only n times because there are only n points, right? So at least the movement, the number of times the pointer here moves or pointer here moves, that's linear. And once you have fixed the window and a point on the left, okay, I need to compute distances in this window, and I know, okay, because of the geometry, that there are at most 8 points in this window. Okay, 4 on top, 4 on bottom. There are at most 8 points. I need to compute these 8 distances, okay, and choose the minimum. That's it. Okay, so let's put all this together and see what we get. Before we do that, I just want to point out one thing. So we needed the points sorted on the y coordinate, right? Now, if we do it on the fly, once we have partitioned, now if we look at points in each band, and now we sort these points along the y coordinate, we would take n log n time. Okay, sorting takes n log n time, and okay, then the recurrence looks like this. Okay, your recurrence would look like Tn equals Tn by 2, well 2Tn by 2 plus n log n, because this sorting will dominate. Okay, once we sort, we can go over them in linear time, but this sorting will dominate and will take n log n time. The solution to this recurrence is still not n log n. Okay, the solution, you can check that. You should try and find out what the solution to this recurrence is. It's n log n squared, and it's not n log n. We would like to be faster. In fact, we would like to get rid of this n log n and replace this with order n, so that overall we get n log n, right? And again, the trick is we pre-sort the points on the x and y coordinates. We do not do it at each recursive call. Okay, so all I want is the point sorted on y coordinates. Suppose I can do it once and for all initially and use this effectively, and that's what I want. Okay, so this n log n for sorting along both x and y coordinates, I do it right at the beginning. Okay, that's a one-time cost. I do not repeat this in each iteration. Okay, it's a one-time cost. I sort them, I am done with, and now I have this sorted order each time I make a recursive call. Okay, so each time I make a recursive call, I have this sorted order in place. In which case, perhaps I can put order n instead of n log n and get an order n log n total time. So let's look at this algorithm. Okay, I've told you all the pieces. We just have to put them together and then analyze the algorithm and see how much time it takes. Okay, so we first sort. So the input, the set of points. So the input is a set of points. Okay, first step 1, sort them on both x and y coordinates. Okay, at this point I would like to make an assumption, which is that each point has every point has a distinct x coordinate and every point has a distinct y coordinate, which means if I take any vertical line, at most one point lies on it. If I take any horizontal line, at most one point lies on it. This is not really a big assumption. I mean, it will not affect us. For instance, what I could do is take the initial set of points. Now perturb each point slightly. Okay, add a small epsilon to each point and sort of move them around a little bit, so that the minimum distance doesn't change. Okay, these perturbations are very, very small. Think of them as very small. The minimum distance could change, but the points do not change. The points which participate in the minimum distance, well, that does not change. Okay, while this perturbation, okay, make sure that if I take any vertical line, 2 points do not lie on this vertical line. Okay, actually the algorithm I'll give right now, we'll assume that no 2 points have the same x coordinate or y coordinate. You can then try and modify this algorithm to work even in the case there are points with the same x coordinate. Okay, so I sort the points on both x and y coordinates. So I have two arrays. The first array where points are sorted on x coordinates. second where points are sorted on y coordinates. Okay, this is done right at the beginning. I am not going to do this recursively. Okay, now the actual procedure starts. So the input to this procedure, okay, the input is points sorted on x and y coordinates. Okay, points sorted on x coordinates, same points sorted on y coordinates. So I have two arrays, two sorted arrays. Okay, this is the input. And what I do, the first step, let me call this step 0. Okay, this is the initialization phase. Okay, step 1 here is divide. Step 2, recurs on both. So divide into halves. Okay, and step 3, put them back. Look at these two solutions, and now look at these points and find the minimum and the return. So broadly, these are the 3 steps. So let's expand on all these steps. Okay, here is step 1. Step 1 is the divide step, right? This is a divide step. Okay, this is a divide step. Well, I have the points sorted on x coordinates, so I can find the leftmost. So since points are sorted on x coordinates, find the leftmost n by 2 elements and rightmost n by 2 points. Okay, these are points. This gives you the 2 points, the 2 sets. Okay, now I need to do this even for the points sorted on y coordinates. Okay, I have 2 arrays, remember. So let me call them let's say A and B. So A is sorted on x coordinates, B is sorted on y coordinates. Splitting A is easy, leftmost n by 2 elements and rightmost n by 2.
So this algorithm that we've just seen is perhaps, as you realize, is more complicated than what we've seen so far. And we've seen all the pieces. Actually, I've given you all the details. What we are going to do now is summarize the whole thing, okay, put them together, and then write out the recurrence, which will not be difficult once we put in all the steps. And once we do that, we'll see that this actually runs in n log n time. Okay. So let's summarize and write down this algorithm in one piece. Okay, the first step is initialization. Okay, it's initialization, and here we sort the points on x coordinate and on y coordinate. Okay, so given this set of input points, we form 2 lists. Okay, we have 2 arrays. One array which will store the points in increasing order of x coordinates. The other array will store the points in increasing order of y coordinates. Okay, and this will be input to the procedure. This initialization is done before we start the algorithm, and with each recursive step, we'll pass down this this information. Okay. Okay. So the next step is the divide step. So it's step 2. It's the divide step. Okay. So here we first look at the median. Okay. So let the value of the median when sorted on x coordinates, okay, let this be, let us say, x median. Okay. So, now we split the input into two parts, okay, points to the left of x median and points to the right of the x median, and then we would like to recurse on these two parts. Okay. To do this, we have to split both the arrays into two parts, both the arrays which is sorted on x coordinates and the array which is sorted on y coordinates. The x coordinate business is easy because you know where the median is, right, it is the n-halved element. So, you just split the array into two parts in a very natural way. For the y coordinates, what you need to do is go through the entire array, okay, look at each point, look at its x coordinate, and then put it into an appropriate array. Okay. So, now let us say these two arrays okay, were points on x coordinate. So, these two arrays are called let us say capital X and capital Y. Okay. So, split, let me write this in a new paper. Okay. So, split x into xl for x left and xr. Okay. Points in XL have their x coordinate less than equal to x median, the median value, and the others are in XR. Other points, XR contains the other points, contains the other points. Okay. Similarly, split y into YL and YR. Okay. Remember, y is sorted on y coordinates, YL and YR will also be sorted on y coordinates. Okay. YL contains the same points as XL, only sorted in y coordinates. Similarly, YR. Okay. So, YR contains the same points as XR. So, this actually divides the input into two parts. Initially, you had these sorted arrays X and Y, and now you have created XL, XR, YL, YR. Okay. The next step is the recurse step. Okay. So, let's write that. So, pass. So, the input is divided into two parts, XL, YL and XR, YR. Okay. These are the same set of points. In XL, they are sorted in increasing x coordinates. In YL, they are sorted in increasing y coordinates, and so on. So, here is the recurse step. Okay. So, you recurse on these two, then you get the shortest, the distance of the shortest, the closest pair on both sides, on either sides of x median. Okay. So, this is the recurse step. So, step 3 is the recurse step. Okay. So, what you get is let us say dl is the distance of the closest pair on input XL, capital XL, capital YL. Similarly, dr is the distance of the closest pair on input XR, YR. Okay, on input XR, YR, the distance of the closest pair on the right hand side is dr, the one on the left hand side is dl. Okay. Okay, so now you look at these two distances, okay, dl and dr, and d, compute d as the minimum of dl and dr. Okay, so that's the next step where you compute the minimum of dl and dr. Okay, now let me quickly review what we have to do next. Around x median, we look at a band of size d on both sides. Okay, so let me draw a picture. So here is x median. Okay, around this on both sides at a distance of d, we look at a band. Okay, this is on the left side, that's on the right side. Now we look at points on these two sides, and we know that if you need to find points which are closer than d, then one point should come from the left, one point should come from the right, and they must be in this band. Okay. So let's first prune XL, YL, XR, YR to only points in these bands. Okay. So that's the next step. So step 4 is putting them together. Is putting the answers together. Okay, so that's the next step. So XL prime will be points from XL whose x coordinates are, well, greater than equal to x median minus d. Okay. So to just look at this figure, this is x median, right? We need points in this range. So any point will have its x coordinate at most x median minus d. Okay, that is step 4. Okay, so similarly, YL prime same y coordinates of the same set of points as in XL prime sorted on y coordinates. Okay, so you get these by pruning XL and YL. So you look at XL and YL and only look at these points in the band, and you remove some of those points. So you're left with XL prime and YL prime. Do a similar thing for the right hand side. So you get XR prime and YR prime. Okay. So XR prime will be points from XR whose x coordinates are, so these are points from XR with x coordinates, okay, which are less than equal to x median plus d. These are points from YR with x coordinates less than equal to x median plus d. So these are the same set of points, only XR prime is sorted on x coordinates, YR prime is sorted on y coordinates. Our focus from now will be on YL prime and YR prime. Okay, we'll only look at these points in increasing y coordinates. Okay, so we are still into step 4. Okay, so let me recall what we do now. So here are the points. Let's say we have XR prime and YR prime, XL prime and YL prime. So I look at, so here is my array XL prime, okay, and here is my array, let's say XR prime. These arrays could have different sizes, okay, because we have proved points from XL and YL, XL and XR. Okay, oh, I'm sorry, this should be YL prime. So because we are going to look at the points in increasing y coordinates. Okay, so YL prime and YR prime are what we are concerned with. So maintain 3 pointers. Okay, let's say P, Q, and R. P will point to something there. Okay, that's P. Q and R will be pointers to YR prime. Okay, so let me quickly recall what we are going to do for each point here. Okay, so here is what we are going to do. So recall that for each point in YL prime, we will find at most 10 points. Okay, this at most 10 follows from a discussion that we did earlier, that in a square with 5 points, there will be 2 who are as close as half the diagonal. Okay, so we will find at most 10 points whose y coordinates are, so supposing this point is okay, so for each point, let's say this point is some x prime y prime. Okay, y coordinates are in the range y prime minus d to y prime plus d. Okay, so we will find these points and then compute the distance from x prime y prime to these points, and this will add 10 more distances. Okay, we do it for every point in this array. Once we do that among all these distances, okay, 10 times the size of the number of points in YL prime, we compute the minimum. Okay, that's our goal. Okay, so a generic step is supposing. So a generic step is this. So I have, let's say I have computed up to this point. Okay, P is done. Here is the latest Q and R. So between Q and R, we find the points with the correct range of y coordinates. Okay. So supposing we have done up to this, now in a generic step, I will raise P by 1, P is P plus 1. Okay. So this moves one step, and now this is your new P. So now correspondingly Q will move and R will move. Okay. So the next step is move Q appropriately. Okay, and then move R appropriately. So what do I mean by appropriately? You increment Q till, okay, if this value is not in the range y prime minus d to y prime plus d, okay, which means it's smaller than y prime minus d. So increment as long as y coordinate is less than y prime minus d. Okay. And similarly you move R, okay, as long as it's less than y prime plus d. Okay, finally when you do this, then you will have these two values for the next value of P, and now you compute the distances, okay, and then compute distances of y prime L P and all points between y prime r q and y prime r small r. Okay. So, then this is the generic step in the loop, put this in a loop, and once you are done, you found these distances, compute the minimum. Okay. So, the last step is compute the minimum of these distances. So, say it's some delta, okay, then return the min of delta and d, okay, and that ends the algorithm. Okay, that ends the algorithm. So, now if you look at the analysis, then there is an initial, so analysis. So, the sorting initially is order n log n. Okay. There are two recursive calls, so that is 2 t n by 2. Okay. And then if you look at the whole analysis, the total time is O n. Okay. So, we can quickly do this. Well, splitting does not take time. The only problem is this pointer manipulation. Okay. In this pointer manipulation, how many times are p, q and r incremented? Well, p can be incremented at most n times, q can be incremented at most n times, r can be incremented at most n times. So, this is order n. The total number of distances we know we calculate is at most order n. Okay. So, that is why this is order n, and T n satisfies this recurrence, and the solution is T n is big O of n log n. Okay. So, this is the analysis of this algorithm, which is pretty simple, and this ends our discussion on divide and conquer. Thank you.